Solenoid. Solenoid. Solenoid is a current carrying coil. Solenoid is a current carrying coil. Current carrying coil or wire wound tightly in the form of a helix. Solenoid is a current carrying wire closely wound in the form of a helix. In the form of a helix from an insulated wire. Solenoid is a current carrying wire closely wound in the form of a helix from an insulated wire such that its length is substantially large or greater than its diameter. Its length is substantially greater than its diameter. This is a diagram of a solenoid or a cylindrical core on which an insulated wire will be closely wound in the form of a helix or cylinder. This is a cylindrical core. On which an insulated wire will be closely wound in the form of a helix. This is the cylindrical core. And we can draw the axis of the cylindrical core or the axis of the solenoid. This is the imaginary axis of the solenoid or the axis of the cylindrical core on which the insulated wire is wound in the shape of cylinder or helix. So here this imaginary line is the axis of the solenoid. This imaginary line is the axis of the solenoid. Now an insulated copper wire or an insulated metallic wire or insulated copper wire is wound in the shape of helix over this cylindrical core as shown in the figure. These are the different turns or obviously the turns of insulated copper wire, and in this case the wire is wound in the shape of a helix or cylinder. This is the insulated copper wire through which a current will be sent, and we can denote the axis of the solenoid. And this is the insulated wire which is closely wound in the shape of a helix over a cylindrical core. And an electric current is sent through this insulated wire. An electric current is sent through this insulated wire, and through each turn the current flows downwards when it is observed from the front face of the solenoid. Here current on the right end of the solenoid flows upwards. I is the electric current which flows through the insulated wire of the solenoid. I is the electric current, and this is the solenoid. L is the length of the solenoid in which there will be n number of turns. Small l is the length of the solenoid. Now we can denote the diameter of the solenoid. Here capital D is the diameter of the solenoid or circular cross section of the solenoid. And in this case, length will be substantially greater than its diameter. Let n be the number of turns of the solenoid. Capital N be the number of turns of the solenoid of length L and diameter capital D, such that its length is substantially greater than its diameter. Obviously, for a solenoid D much less than L, that means diameter is much less than the length of the solenoid. The term solenoid was coined in 1823. The term solenoid was coined in 1823 by French physicist André Marie Ampère. By French physicist André Marie Ampère. The term solenoid was coined in 1823 by French physicist André Marie Ampère. Now we can draw the imaginary magnetic field lines produced inside and outside the solenoid. This circular or elliptical magnetic field lines are due to a solenoid. So these are the two circular or elliptical magnetic field lines produced due to a flow of current through a solenoid. We can denote more magnetic field lines, and magnetic field lines inside the solenoid are almost parallel to each other. The magnetic field lines inside the solenoid, magnetic field lines which are almost parallel inside the solenoid. In the diagram, obviously the magnetic field lines which are almost parallel inside the solenoid. That's why we can say that solenoid produces uniform magnetic field or produces uniform magnetic flux density inside the solenoid. A solenoid can produce uniform magnetic field in the space inside the solenoid, in the space inside the cylindrical coil or inside the solenoid. The magnetic field lines are almost parallel inside the solenoid. That's why you can say that a solenoid can produce uniform magnetic field. A solenoid can produce a uniform magnetic field in the space inside the solenoid. But the density of magnetic field lines outside the solenoid, that is the magnetic flux density under bracket capital B, or magnetic field intensity outside the solenoid is greatly reduced. That is magnetic field induction under bracket B. Magnetic field induction under bracket B becomes zero as the area outside the solenoid, is much greater than the area inside the solenoid. That's why density of magnetic field lines, that is magnetic flux density outside the solenoid, is greatly reduced in comparison to the magnetic flux density inside the solenoid. So we can assume that magnetic flux density or magnetic field induction is zero outside the solenoid, but the solenoid produces a definite magnetic field induction or magnetic flux density inside the solenoid. Here B naught is equal to 0 outside the solenoid, but B is greater than 0 inside the solenoid. As area of the space outside the solenoid is very large, that's why magnetic field induction outside the solenoid is 0. That means B0 is equal to 0. But magnetic field induction is not 0 in a space inside the solenoid. Now we can draw the magnetic field lines inside and outside a solenoid. So these are the magnetic field lines, circular or elliptical magnetic field lines produced due to flow of current through a solenoid. This is the magnetic field lines in a space outside the solenoid. In a space outside the solenoid. Now, an insulated wire, we can denote or draw the solenoid actually. So these are the magnetic field lines inside the solenoid which are parallel to each other. These magnetic field lines inside the solenoid are parallel to each other. So here these are the magnetic field lines which are parallel to each other, and these magnetic field lines exist inside the solenoid. Magnetic field lines which are parallel to each other exist inside the solenoid. Now we can denote insulated wire which is tightly wound in the form of a helix, and this is insulated copper wire which is wound in the form of a helix. This is the insulated wire which are wound in the form of a helix, and a current I is sent through this insulated copper wire. This is the cylinder obviously over which the insulated copper wire is wound, and magnetic field lines inside the solenoid are parallel to each other. In this case, the magnetic field lines inside the solenoid or magnetic field inside the solenoid is uniform because magnetic field lines inside the solenoid are parallel to each other. Now we can describe the uses of a solenoid. Uses of a solenoid. Solenoid is an output device. Solenoid is an electric output device. That converts electrical energy into mechanical energy. Solenoid is an electric output device that converts electrical energy into mechanical energy, that is, into linear mechanical force. Solenoid can also convert linear mechanical force. Obviously can produce the linear mechanical force using electrical energy. They are utilized in wide range of residential equipments. Including door locks, washing machine or doorbells. Also doorbells, washing machine, locking system, etc. They are utilized in wide range of residential equipments including doorbells, washing machine, locking system, etc. Full stop. The main use of solenoid is a switch for power. Solenoid is a device. Solenoid is a device comprised of a coil of wire Solenoid is a device comprised of a coil of wire and a movable plunger when an electric current is introduced. When an electric current is introduced, magnetic field, magnetic field is formed. Magnetic field is formed inside the solenoid. A uniform magnetic field, not only magnetic field, it should be rather uniform magnetic field. Magnetic field is formed. Around a uniform magnetic field is formed around the coil, which draws the plunger in the solenoid. That means due to flow of current, a magnetic field is produced, and the plunger moves inside the solenoid as it experiences a mechanical movable force. More simply, a solenoid converts electrical energy into mechanical energy. In the diagram, a solenoid or cylindrical coil is connected to a battery, which is in green color, and solenoid is made of a copper wire. This is a solenoid. That means an insulated copper wire is wound in the form of a helix, and that is the solenoid. And solenoid is connected to a battery. Left end of the solenoid is connected to positive terminal of the battery, and the other end is connected to the negative terminal of the battery. If the battery sends I amount of current, in that case south pole and N pole or north pole will be induced at two different ends of the solenoid, and the plunger placed nearer to the north pole of the solenoid, plunger or cylindrical, a cylinder of soft iron core is placed nearer to the north pole of the solenoid, will move inside the solenoid as it experiences a mechanical force. In this case, obviously, the magnetic field, due to the flow of current through the solenoid, a magnetic field B is set up, uniform magnetic field is produced, and that attracts the cylindrical the cylinder of soft iron core, or attracts the plunger inside the solenoid. If the circuit is closed, in that case the battery sends a current I through the solenoid. South pole and north pole will be induced at two different ends of the solenoid. Here in the diagram, if the circuit is closed and the battery sends the current to the solenoid or coil, and the plunger will move into the solenoid as shown in the figure. In the diagram, a magnet having blue colored south pole and red colored north pole is placed as plunger nearer to the north pole of the solenoid. Now, if the circuit is closed, the battery sends the current to the cylindrical coil or the solenoid, and south pole and north pole will be induced, and that magnetic field inside the solenoid will attract the cylindrical magnet. That means the plunger moves into the solenoid. If the battery connection is reversed, that means if the current is sent in the opposite direction, the magnetic polarity of the solenoid will be changed, and the magnet will be repelled, and it will move outside the solenoid. So here we have explained in what way solenoid converts electrical energy into mechanical energy. That means current is sent to the solenoid, and uniform magnetic field is produced inside the solenoid, due to which a plunger or a metallic cylindrical core will be attracted inside the solenoid. Now we have to know the expression of magnetic field induction, that is magnetic flux density inside the solenoid in different cases. What will be the expression of magnetic field induction or magnetic flux density inside the solenoid? Inside inside a solenoid. Now we can draw a diagram of a solenoid. We can draw a diagram of a solenoid in which an insulated copper wire will be wound tightly in the form of a helix. This is the axis of the solenoid. This is the axis of the solenoid about which an insulated wire will be wound in the form of a helix, and that will be a solenoid. This is the axis of the solenoid. Axis of the solenoid. Now, an insulated copper wire is wound about this axis for having a solenoid. So this is the insulated wire or insulated copper wire which is wound in this way, and this is tightly wound in the form of a helix. And we shall get a solenoid which produces strong uniform magnetic field inside the solenoid, and this solenoid converts electrical energy into mechanical energy. A uniform magnetic field is produced, and a plunger or a metallic cylindrical core will move into the solenoid or will move away from the solenoid. This is a diagram of solenoid or cylindrical coil. Solenoid with vacuum. So obviously the internal medium will be vacuum, or the core is made of vacuum. So the medium inside the solenoid is vacuum, and the medium outside the solenoid is also vacuum. And we can denote different turns: first, second, third, nth turn, and L. Small l is the length of the solenoid. We can denote a point P. At the point P, a magnetic field or uniform magnetic field of flux density B will act towards left. That means will act from magnetic south pole to north pole of the solenoid. So here B is the magnetic flux density or magnetic field induction at the point P on the axis of the solenoid and also inside the solenoid. B is the magnetic flux density or magnetic field induction at the point P on the axis of the solenoid, such that the solenoid encloses vacuum as its core, and the surrounding medium is also vacuum. The magnetic field induction, that is the magnetic flux density at a point P inside the solenoid with vacuum as its core, is given by B is equal mu 0 n by L into I. Mu 0 n by L into I, where I is the current flowing through the solenoid, and n by L is the number of turns of the solenoid. N by L is the number of turns of the solenoid. Here south pole and north pole will be induced at two ends. So B is equal mu 0 small ni. B is equal mu 0 small ni. That is the expression of magnetic flux density at the point P on the axis of the solenoid and also inside the solenoid. And this magnetic field induction acts from south pole to north pole inside the solenoid, where the number of turns per unit length of the solenoid is under bracket small n, which is equal to n by L, where n is the total number of turns of the solenoid and L, small l, is the length of the solenoid. So B is equal to mu 0 small n capital I, mu 0 ni. That is the expression of magnetic flux density at a point inside the solenoid. Now we can consider a cylinder with a cylindrical core of soft iron. This is the cylindrical core having permeability, magnetic permeability mu, and an insulated copper wire is wound tightly in a shape of helix over this cylindrical core. In this way, the insulated wire is wound tightly in a shape of a helix over a cylindrical core of magnetic permeability mu. A current I is sent through the wire, and this current will produce a uniform magnetic field at a point inside the solenoid. This is the imaginary axis of the solenoid inside the cylindrical core. The surrounding medium is vacuum. Of magnetic permeability mu 0. Here, the surrounding medium of the solenoid with a cylindrical core is vacuum having magnetic permeability mu 0, and mu is the magnetic permeability of the cylindrical core. Magnetic field induction at P is B, which acts from south pole to north pole of the solenoid. We can denote the direction of current I through each turn of the solenoid, and current flows downwards through each turn of the solenoid, and the left end of the solenoid is south pole and a magnetic north pole is induced at the right end of the solenoid. And this is the solenoid with a core of magnetic permeability mu. When a ferromagnetic cylindrical core of magnetic permeability mu is inserted in a solenoid carrying current I, the magnetic flux density inside the solenoid is given by B equal mu 0 mu effective under bracket n by L into I, where I is the current flowing through the solenoid, L is the length of the solenoid, and N is the number of turns of the solenoid. N is the number of turns of the solenoid, and L is the length of the solenoid. Where mu effective is the effective magnetic permeability of the cylindrical core. Mu effective is the effective permeability of the cylindrical core of the solenoid, such that mu is equal mu 0 mu effective. Mu equal mu 0 mu effective, where mu is the magnetic permeability of the core. And the expression of mu effective or effective magnetic permeability of the cylindrical core is given by mu r divided by 1 plus k under bracket mu r minus 1. Mu effective is equal to mu r divided by 1 plus k under bracket mu r minus 1, where mu r is the relative magnetic permeability of the cylindrical core, and we get mu effective as the effective magnetic permeability of the cylindrical core. K is the demagnetization factor of the cylindrical core. And mu r is the relative magnetic permeability of the core. Mu r is the relative magnetic permeability of the cylindrical core. Finally, the magnetic field induction at a point inside the solenoid is B equal mu n by L into I. Where mu is numerically equal to mu 0 into mu effective. and B is mu 0 mu effective under bracket n by L into I, or B is equal mu n by L into I, where mu is numerically equal to the product of mu 0 and mu effective. Mu is numerically equal to mu 0 into mu effective. Mu is the magnetic permeability of the cylindrical core, and mu effective is the effective magnetic permeability of the core. And B is equal mu under bracket n by L into I, which is the magnetic flux density or magnetic field induction at a point inside the solenoid with a cylindrical core. Inside the solenoid with a cylindrical core. B is equal mu under bracket n by L into I, which is the magnetic flux density inside a solenoid with a cylindrical core. Now we can discuss the determination of nature of magnetic pole induced at two ends of a current carrying solenoid. Determination of nature of magnetic pole of determination of nature of magnetic pole induced at the two ends or at the two terminals of a current carrying solenoid. Determination of nature of magnetic pole induced at the two ends of a solenoid. This is a solenoid or an insulated copper wire which is wound in a shape of helix, and we can denote the order of the number of turns of the solenoid. N is the number of turns of the solenoid, and the length of the solenoid is small l, and a current I is sent through the wire, which will appear to flow clockwise at the left end of the solenoid. That's why south pole will be induced at the left end, through which current will appear to flow clockwise, and that is according to clock rule. So this is the end or left end of the solenoid through which current flows clockwise. Current flows clockwise if it is observed from left end, and magnetic south pole is induced at the left end, through which current is appearing to flow clockwise. And this nature of magnetic pole is determined as according to the clock rule. Similarly, we can consider the other end, that means right end of the solenoid, through which current appears to be passing anti-clockwise, and the magnetic north pole is induced at that end. So here a solenoid produces a strong magnetic field at a point inside the solenoid, and the solenoid will behave as a magnetic bar having south pole and north pole separated by a definite distance, and magnetic field induction B acts from south pole to north pole at a point inside the solenoid. Now we consider a solenoid or cylindrical coil or a wire which is wound tightly in a shape of helix, which is connected to the two terminals of a battery. So this is a solenoid. Or a cylindrical coil which is connected to the two terminals of the battery, and the battery sends a current I, and that current I flows through the solenoid, and which is shown in the figure. That current I flows through the solenoid in this way, and this current I will appear to flow clockwise, and at the other end the current I will appear to flow anticlockwise. And at the left end, magnetic south pole is induced. At the left end of the solenoid, magnetic south pole will be induced as the current will appear to flow clockwise. The current, in this case, the current which is coming from the battery will appear to flow through the turn at the left end clockwise. And in this case, we can write what that is the current, that is the end. This is the end in which the current, appears to flow clockwise, and a magnetic south pole is induced at that end. The left end in which the current appears to be passing clockwise. At the other end, magnetic north pole is induced. That means at the right end of the solenoid, magnetic north pole is induced, because this is the end, or the right end of the solenoid, in which the current flows anticlockwise. The right end, or the end of the solenoid in which the current flows anticlockwise, and magnetic north pole will be induced at that end. Hence, at the point P, magnetic field induction or magnetic flux density B will act from south pole to north pole. Now this is a solenoid to which a battery will be connected. This is a solenoid or cylindrical coil, and the battery will send a current through the solenoid, and we get this type of magnetic field lines, and magnetic field lines will be parallel to each other inside the solenoid. And this solenoid will have south pole and north pole, and it will behave as a bar magnet. And if we observe from the right end of the solenoid, the current will appear to flow anticlockwise, and a magnetic north pole will be induced at the right end of the solenoid. Here the current is flowing anticlockwise. Similarly, if we observe from the left end, in that case the current is appearing to flow clockwise. The current is flowing clockwise, and a magnetic south pole is induced at the left end of the solenoid. That's why the solenoid will have south pole and north pole. And this will behave as a bar magnet. Solenoid may also refers to an actuator which uses an electromagnet to convert electrical energy into mechanical energy. Solenoid may also refers to an actuator which uses an electromagnet to convert electrical energy into mechanical energy. Solenoid can be used as a starter relay. Which is an electromagnetically operated switch. Solenoid can be used as a starter relay, which is an electromagnetically operated switch. And solenoid can be used for wireless power transmission. We can discuss another use of solenoid, that is solenoid bolt, which is a type of electronic mechanical lock, which is a type of electronic mechanical locking system. Sophisticated solenoid bolt locks. Sophisticated solenoid bolt locks. Bolt locks may provide access control. Sophisticated solenoid bolt locks may provide access control for high security sites. That means the another use is what solenoid bolt is a special type of electronic mechanical locking system, and this sophisticated solenoid bolt locks may provide access control for high security sites. So these are the three uses. So number one use is what solenoid can be used as starter relay, which is an electromagnetically operated switch, and it can be used as wireless power transmission solenoid, and it can be used as solenoid bolt, which is a special type of electronic mechanical locking system.